Let's look at some more examples. Find the area, I remember area means integral, of the region bounded by y equals x minus 2 and y equals x cubed minus 3x squared plus x with a calculator. With a calculator doesn't mean that we have to use a calculator to help us graph, but we're going to have to do other things. We'll see. Let's go ahead and begin by graphing the linear function. Y is by itself. This is a function of x. Start down 2 units, and it's a straight line with a slope of 1. So I'm going to find all those points, and there's my line. Now, earlier, I found the points, and I'm going to tell you what they are. This is not one of your basic cubic functions, so we might need to do some plugging and chugging. At -1, I got 1, 2, 3, 4, 5. I got -5, 0, 0, 1, -1, and 2, -2, 3, 3. With those points, I can get a basic picture of what this graph looks like. Now, shading the regions bounded by these two curves, notice I said regions because here's an enclosed region that connects the blue and the green, and here's an enclosed region that also connects or touches the blue and the green. Because these are functions of x, I should be able to go top minus bottom. So let's see, top is blue, bottom is green. Top is blue, bottom is green, until I switch over to the other region. Top is green, bottom is blue. So if I'm working as functions of x, top minus bottom, as functions of x, I'm going to have to use two regions, which is going to mean two integrals. So I'm going to do the integral of the first region, where the top is the blue function, or the cubic, x cubed minus 3x squared plus x, and then subtract from that the lower one, x minus 2, both with respect to x. Combine that with, add that to, the integral. Now the green one, or the linear one, is on top. X minus 2 minus the cubic function, because now it's on the bottom, or lower. Now I have to figure out my limits. Where do the regions start and stop? Now, sometimes it's obvious, like not here, because at -1, notice that I have two different y values, one for the green curve and one for the blue curve. So although it looks like it intersects there, it really intersects slightly after -1. This point, they both landed on at the same place. So x equals 1 is an intersection point. Here's another place where it looks kind of like it's almost 3, but not quite. So now we're going to take out our calculator, and we're going to plug into y equals the two functions. I've done that already, and I examine the graph, and I can see approximately where they intersect, but we want to calculate it exactly. So I do second calculate. I find intersect, scroll down or hit choice 5. My cursor's already over here, so I'm going to find that one first. So if I go down or up, it switches curves. If it says first curve and it's near my intersection, I press enter. Second curve is still near my intersection, press enter and enter one more time. That intersection is at 2.732. We're always going to carry it out to at least 3 numbers after the decimal point, if not more. The first intersection, well, let's go ahead and now figure that. So again, I do second calculate, choose choice 5. But I've got to scroll over to the other intersection point. Notice that I'm going to the left. Up or down switches curves, but left or right moves it over to the position on the curve that I need. Press enter when I get there, enter again, enter a third time. The intersection is at -0.732, or carry it out to more places if that's helpful. So I see the first region starts at this x value, -0.732, and ends at the next x intersection, 1. The second region starts where the first one left off and ends at 2.732. Now I can go ahead and evaluate the integral by taking the antiderivative or using a calculator. Any way that I choose to do it, I get approximately 4.500. Let's take a look at another one. Find the area, I remember area means integral, of the region bounded by y equals x minus 1 and y squared equals 2x plus 6. Let's go ahead and graph both of those, beginning with y equals x minus 1. I'm going to go down 1, and my slope is up 1 over 1, up 1 over 1. And this is a pretty basic function. So there I've got my straight line. Now the next one is not so basic. Y squared equals 2x plus 6, y squared. Now hopefully you remember that that is going to create a sideways parabola, something like this. So you might want to pick points for x or y, plug it in, and calculate the value for the other half of the coordinate. Or you can solve for x. So subtracting 6 and dividing by 2, we get x equals 1/2 y squared minus 3. If I solve for x, then I think about how I usually graph a parabola and just do it sideways. For example, minus 3 means I shift the vertex in the negative direction 3 units. So in the x direction negatively would be 1, 2, 3 units. Then it's a parabola that opens in the positive direction, that'll be to the right, but 1/2 is much. So if I normally go 2 out and 2 squared is 4, half of 4 is 2. Same thing down here. If I normally go 1, 2, 3, 4 out and 4 squared is 16, half of 16 is 8. 1, 2, 3, 4, 5, 6, 7, 8. And same thing symmetrically down here. Now, picking points, plugging and chugging will also work. So don't feel too stressed about graphing. Now let's shade the region bounded by those two curves. There it is. Now let's examine if I do top minus bottom. Over here where I start shading, the top is green, the bottom is green. Top is green, the bottom is point. What? It's both. Here, top is green, bottom is blue. Top is green, bottom is blue. It changes depending on where I am in the region. So now let's think about this. Remember how we had to solve for x to be able to graph this a little bit more logistically or logically? Logically. Well, we want to think about how it's a sideways parabola. It's not a function. See, it fails the vertical line test. It's not a function of x, but if I do the horizontal line test, they both can be functions of y. So if we're thinking about, are they functions? Can they be written as functions of y? Then I want to think about that I might be doing the integral of what's on the right minus what's on the left. Let's practice shading that way. So on the right would be blue, left would be green. If I move lower, right is blue, left is green. If I continue to move down, it's always that the right is blue and left is green. Well, that's going to be much easier to do because it doesn't switch. So I'm going to use right minus left, which means I do want functions of y. If I want functions of y, that means I must solve for x, get x by itself. Already did that with the parabola. Now let's do that with the line. X by itself makes y plus 1. So I'm going to write the integral. The function on the right is the linear one, y plus 1, minus the function on the left is the parabola or the quadratic 1/2 y squared minus 3. I have to write that it's with respect to y, but that doesn't really change how I integrate. It's just a different letter. Now also what's important here is that these limits have to be y values. If these are y's, these have to be y also. So I look from low to high. Where does my region start? 1, 2. That's -2. Where does my region end? How high does it go? 1, 2, 3, 4. So starting at -2 and ending at 4. I can do this by taking antiderivatives or by plugging into my calculator. Depending on what's allowed, I get 18. Let's examine one more example that's from an AP test and written a little differently. Consider the curve y squared equals 4 plus x and chord AB. So you have to remember that a chord is a segment, which remember is part of a line, joining these 2 points on the curve. Find the area. What does area mean? Integral of the region R enclosed by the curve and chord AB. So let's start by graphing those two. Now, just like we did before, it's going to be easier to think of this as a function of y. So solving for x, y squared minus 4, I know that it's a parabola opening in the positive direction of x and shifted to the -4 of x. So 1, 2, 3, 4. Up 1, 1 squared is 1. Up 2, 2 squared is 4. So I get a parabola like this, which the other half would look like that. Now, why don't I have any region here? Because I'm not going to need it. Let's see why. The chord joined by those 2 points, -4, 0. 1, 2, 3, 4, -4, 0, and 0, 2, 0, 2. So connecting those points. Now it's just a segment really, but it's easier if I graph more of the line to examine where the region is. The region has to touch both of those lines, and there it is. There's that little region touching the blue and the green. So I think about top minus bottom. Yep, top is always blue, bottom is always green if I shade that way. I prefer to do top minus bottom if I can. So I think about doing top minus bottom, and I remember that that means I need dx. I need a function of x, but that would mean y has to be by itself. I need y equals and then everything else on the other side. But then I'd have to have y equals plus or minus the square root of 4 plus x. Well, maybe that's not such a big deal. If I solved for y all by itself, y equals plus or minus the square root of 4 plus x, and actually, I know that I only need the top of the parabola, so really it's just the positive square root of 4 plus x. So I could do the integral of the blue, or the parabola, square root of 4 plus x, minus what's on the bottom, the line. But I don't have a line, so I have to come up with that equation so I can plug it into my integral. So that line I see has a y-intercept of 2 and a slope of up 2 over 4, or simplified to 1/2. So using slope-intercept form, which is going to be very easy here, 1/2 x plus 2, there's the equation of my line. So 1/2 x plus 2, and then I'm working with respect to x. If I'm working with respect to x, these must be x's. So my x starts at -4 and stops at 0. -4 to 0. I could plug that in a calculator, depending if I can use a calculator to integrate or evaluate it by hand, and I get 1 1/3. But the point today is, how do we set up the integral? So let's think about another option. If I choose to say right minus left, and why did I think of doing that? Because remember, to graph it, we solved for x. We made it a function of y. If it's right minus left, we need dy. So that means I need it to be x equals. And that's what I had at first in order to graph. Well, right minus left, right is green, left is blue. Always right is green, left is blue. So I could choose right minus left, And then I could use the line on the right, but if I did that, I have to solve for x. Subtract 2 and multiply by 2. So x equals 2y minus 4. On the right is that line. So first it's going to be the 2y minus 4, and then on the left, what I used solving for x, y squared minus 4. Subtract the right minus the left with respect to y, and remember these limits now must be y values. So the lowest the graph goes is 0. The highest the graph goes is 2. 0 to 2. If I evaluate this using antiderivatives, I also get 1 1/3. Again, the point is not necessarily how we get that final answer, it's how we set up that integral. Sometimes it's easier in terms of x, sometimes it's easier in terms of y, and sometimes it's an option. Hope you had fun today.